first of all, I need to make sure that we understand the terminology that I'm using here. The process of taking a derivative is called differentiation. All right, so you'll hear things like differential calculus, or differentiation is the verb to take a derivative. That means the same thing as taking derivatives. All right, so when I use that term, that refers to the derivative half of calculus, or the tangent line problem part of calculus. What we've done so far with derivatives and differentiation has been, on a very basic level, using limits to find the slope of a tangent line. Now, we can do this pretty easily with pretty basic functions. Finding the slope of a tangent line for a polynomial, especially low-degree polynomials, we end up with limits that are easy to simplify and evaluate. But we're going to start running into, very quickly, a lot more complicated functions, like trig functions and exponential functions, logarithmic functions, or even polynomials of high degrees, where using that limit definition is just going to be really annoying. So we're going to see things like these. This first one is one that we've done, where if we want to take the derivative of x squared, we use a limit definition, and it looks like this. This is a pretty easy thing to evaluate. But if we want to do like x to the ninth, we would have to expand x plus delta x to the ninth power, and then expand that to simplify this expression. So even just a simple power expression is not very simple to evaluate using that limit definition. If we get to things like the sine function or other trig functions, how many of you know off the top of your head what the sine of x plus delta x is? Do you?
No.
Okay. What would we have to use there? See if you even remember that. We'd have to use the sum formula for sine, right? You guys remember those? Sum and difference formulas and all that stuff. Half angle formulas, double angle formulas. So this right here would involve an expression with sines and cosines of x and delta x. But that's not an identity that we probably have memorized. So simplifying an expression like this would require that, and we don't really know it off the top of our head. Something that's just a little bit more complicated, like cosine of 2x squared, gets way more complicated using the limit definition. So the point I'm trying to make here is the limit definition is great. That's where all of this is going to build from. But if we can come up with some other methods that are going to make these things easier, like taking the derivative of an x squared or taking the derivative of sine, if we can come up with ways of making these easier, it's going to be really useful for us. So we built our foundation using that limit definition. We're going to come up with some methods that we can differentiate with or take derivatives with that are going to allow us to do it with more complicated functions like this one or even these two, and do it fairly easily, relatively easily, especially compared to what we would have to do with the limit. All right, so that's going to be our goal over the next couple of weeks, is we're going to talk about differentiation methods and basically shortcuts for taking the derivatives of different types of functions. All right, I know some of you know some of those shortcuts already, particularly the power rule, which would allow you to take the derivative of this. And we're going to talk about that one today, but we're going to get into all different kinds of derivatives and how we would simplify those or how we would differentiate those.